to the scientific committee for the invitation to talk in this meeting. Well, I will continue with the non-holonomic systems that Luis introduced and this Hamiltonization problem. So our goal is to study the geometry of the reduced almost Poisson bracket describing the dynamics. This is our goal. So we are starting with a brief introduction to non-holonomic systems, then the motivation, that is this Hamiltonization problem. Then we are going to define these gauge transformations and study some examples. And finally, we are going to study the almost symplectic leaves that we have and the Lagrange-Routh equations. So the work, my talk is based on these 3 papers that I will use tools of the 3 papers. One is in collaboration with Luis Garcia Naranjo, the other one with Oscar Fernandez, and the other one alone. So let's start defining what a non-holonomic system is. First, this is only to set a notation. A Hamiltonian system on the cotangent bundle is described by this vector field that satisfies that equation where h is the Hamiltonian function. And now a non-holonomic system is a mechanical system with constraints in the velocities. For example, all the examples that Luis worked, that, for example, a ball rolling on a plane that does not slide. So we have a relation between the angular velocity and the translational velocity of the solid. So if we have these constraints on the velocities, we have a submanifold distribution, of the tangent bundle. This is the space of permitted velocities. That is a non-integrable distribution. And since we want to work on the Hamiltonian side, we are going to take into account this M, which is the image by the Legendre transformation of D. So this M will be is submanifold of the cotangent bundle, and we are going to work on this M, and we are going to define this distribution C that is the pre-image of D. So our objects up to now are this manifold, this submanifold of the cotangent bundle, plus this is the canonical 2 form restricted to M, and this distribution on M. So this is a presymplectic manifold, but since the restriction of this 2 form to C is non-degenerate, we have a well-defined vector field defined by this equation, where this is the Hamiltonian restricted to our submanifold M. And this is the non-holonomic vector field, and will describe the non-holonomic dynamics. So this is our base equation describing the non-holonomic dynamics. Can you see that we are restricting the 2 form to the submanifold M, and also both sides of the equation are restricted to this distribution C. So this equation defines a bracket on M. This is an almost Poisson bracket that is defined by this relation. So this bracket was originally defined by, here we have Juan Carlos, Manuel de Leon, and David, and many other people like Marle also work with this bracket. This is an almost Poisson bracket that does not satisfy the Jacobi identity. And the equations of motion are described in this sense. So this is our Hamiltonian restricted to M, and this is our non-holonomic vector field. So now we are going to, one observation is that C, this distribution, really is the distribution generated by all Hamiltonian vector fields of this bracket. So if we compute all the Hamiltonian vector fields of the non-holonomic bracket, this distribution C will be generated by those brackets. So it's important to note that C is not integrable, so we are not having this involutivity property that the Lie bracket of two Hamiltonian vector fields will be again a Hamiltonian vector field. This is not true in this non-holonomic bracket. So this is what we are going to do. We are going to suppose that the system has a Lie group, has a symmetry, and now if we have this bracket on M, the non-holonomic bracket, it's very easy to reduce everything to the reduced space working with brackets. So what we are going to do is just to define a reduced bracket on this reduced manifold M mod G. And of course, we can define the equations of motion now are going to be the reduced equations of motion. This is very important to work with reduced systems, since here we are having less variables than up here. So that's why it's important to reduce. And for us, it's not only important because of that, it's also important because we have some change of properties in this reduction process. And we are interested in that change of properties. What I mean is this bracket is not Poisson and won't be Poisson by any chances, unless you are working with holonomic systems. But this bracket has better properties than this one. And these are the questions. Are the reduced equations Hamiltonian? Does this reduced bracket satisfy the Jacobi identity? These are the questions, but only after this reduction. So this is what I will try to study. And what we are going to do is to try to study this Jacobi identity for these reduced brackets here. So computing a Jacobi identity is very difficult. We have to take all the functions and try and start to computing. So what we are going to do is try to find a formula for the Jacobi identity for non-holonomic systems. So first of all, what we are going to do is I will present different brackets that can be used to describe the dynamics. Of course, the first one is a Poisson bracket that we already know that non-holonomic systems are not described by a Poisson bracket, but maybe after reduction by symmetries, we have a Poisson bracket describing the dynamics. You have to have in mind that a Poisson bracket has a foliation of symplectic leaves. On the other extreme, we have an almost Poisson bracket, which is a bracket that does not satisfy the Jacobi identity. And this characteristic distribution, the distribution generated by the Hamiltonian vector fields, is not integrable. It's not necessarily integrable. But we have something in between both of them that are called these twisted Poisson brackets that were defined by Strobel and also by Alan Weinstein and Severa. These brackets have this property, that the Jacobi identity is controlled by a 3-form. So this bracket it's very nice because it admits foliation, so the characteristic distribution is integrable, but on each leaf we will have a 2-form that is not necessarily closed. So here we have a symplectic foliation, here we have an almost symplectic foliation, and here we don't have anything. Non-holonomic brackets are in this group, that we don't have anything. So let's start studying our Jacobiators. A non-holonomic system is defined on a submanifold, on this submanifold M, and the non-holonomic bracket, and we are going to suppose that we have a G action that leaves everything invariant, and we will work with this dimension assumption that also Luis mentioned. This dimension assumption is that the vertical space is completing the space of permitted, in this case, of restrictions. So the vertical is completing the space of restrictions, and we're going to split our tangent bundle into this distribution, the characteristic distribution, and something else that is vertical. With this splitting, we can define a 3-form that depends on the canonical momentum map and on this K that is some kind of curvature. It's not truly curvature, but I am copying the same definition of a curvature. But it's not the same because this is not a vertical space of a Lie group. So this is not a truly curvature. But we can define this G-valued 2-form, we can define this 3-form, and then we can write the Jacobiator formula for the reduced brackets. So this Jacobiator formula, it involves this 3-form, but can you see that this is the reduced bracket, and here we have the non-holonomic, the Hamiltonian vector fields, but it's everything defined upstairs. Why? Because this 3-form might not be basic, so maybe this 3-form is not defined in terms of the reduced variables. That's why I have to pull everything upstairs. So, but using this formula. First, an observation. This formula generalizes the works of Marsden and Kuhn, which was the Jacobiator in coordinates, and also generalized the works of Bates and Sniatyski. Okay, so now we are going to use this formula to have some to analyze some examples. So first we see from the formula that if this thing is 0, then the bracket is automatically Poisson. Can you see this from here? If this is 0, this will be Poisson. But also, if this 3 form is closed and basic, then this bracket will be twisted Poisson. So the bracket will admit almost symplectic foliation. And this will be the Jacobiator. So if you are looking for a system that admits Hamiltonization after a reparametrization of time, you have to look into these brackets, because these are the brackets, the twisted Poisson brackets, that will admit that, if you're lucky, will admit reparametrization of time. So, very simple example, the vertical rolling disk, you can compute this 3 form. This 3 form is 0. So automatically this example will be Poisson after the reduction. I am always talking about the systems after the reduction. Then the snakeboard. The snakeboard is a kind of skateboard that you produce some movement with your body. And the skateboard, after a reduction by symmetries, you can compute this 3 form. And this 3 form is basic and closed. In this case, it's also exact. So the system is twisted Poisson. So the system admits a foliation with almost symplectic leaves. And finally, the non-holonomic particle, that this 3 form is not basic, but is 0 over these Hamiltonian vector fields. So the bracket will be Poisson. So I continue working with examples, and I took a little more interesting examples. The Chaplygin ball, this was worked with Luis. We computed, you can compute the 3 form, it's not basic. So apparently we cannot do anything. And next example is this cylinder, a ball rolling on a cylinder, that you compute the 3 form and is not basic either. So what to do when you are here? Our question was, are there more brackets describing the dynamics? And why do I have to take a bracket that depends on the canonical 2 form? Remember that this was the definition of the non-holonomic bracket, where this bracket, this 2 form it was the canonical 2 form restricted to the submanifold M. So why do I have to choose always the canonical 2 form? Let's choose another 2 form. Let's choose a deformation. This is the canonical 2 form plus a term. And compute this bracket, the bracket given by this formula. This originally was an operation defined also by Alan Weinstein that is called gauge transformations. And in this sense, we can produce a lot of different brackets. But of course, I am describing dynamics. So I want a bracket describing the dynamics. I don't want just any bracket that is a deformation. So I will put two constraints. First, that this is non-degenerate. This 2 form is only to have a well-defined bracket. And this is a very important dynamical condition that I am putting on B. I need this B, I need this condition, so B does not see the dynamics. B does not modify the dynamics. So if we have this condition, then this whole family will describe the dynamics, and that is what we called the dynamical gauge transformations in our work with Luis. So this is the idea. We have a non-holonomic system, we have the classical non-holonomic bracket, and now we are going to compute all the possible dynamical gauge transformations. We are going to obtain a whole family here, and then we can reduce this family and obtain a new family of reduced brackets describing the dynamics. This is much better because now we can look into a whole family for a bracket with nice conditions. So the idea is looking into that family. The first question is, okay, now I have to compute the Jacobiator of this family to see when it's 0 or not 0. And luckily, if we compute the Jacobiator of the guys here, The only modification that we have is we have the 3 form here, and here we have the differential of B. So now this gives another way, another condition to look for the 2 form B. We want a 2 form that the differential of B plus this is 0 over the Hamiltonian vector fields, or basic. That is, that depends only on the reduced variables. So these are the things that I will ask for B. This condition, then the bracket will be Poisson, or this condition, then the bracket will be twisted Poisson. We'll have an almost symplectic foliation, a bracket that admits almost symplectic foliation. So now we have 2 conditions that has to be satisfied by the 2 form B. One is completely dynamical, and the other one is completely geometrical. The completely dynamical is there is a dynamical gauge that B does not see the Hamiltonian vector field. And the completely geometrical is that B has to satisfy one of these conditions. And putting together a dynamical and a geometrical condition is very difficult when you are computing examples. So this is our examples. The idea is that we are going to look for a dynamical gauge such that this 3 form is basic or 0. And then the first example is the ball on a cylinder. This ball on a cylinder, I computed already knowing the whole machinery, already knowing all the formulas. And this is the example that we worked with Luis, and Luis was the one that started studying this example and found this B. And this example was worth doing a lot of computations. And what I did here was I looked for a B such that this was 0. So the bracket, this bracket, there is one bracket here, there is Poisson. But if you compute this bracket here, it's not Poisson, does not admit a foliation. So it's very important to deform the bracket to obtain one that is Poisson. If you compute here, this really does not admit a foliation. And what I did to compute this 2 form B is I took the dynamical condition. What is a dynamical property of the system is conserved quantities. And what I did is to transform my conserved quantity into a Casimir of this bracket. So I forced this bracket to have as a Casimir the conserved quantity of the system. This is what I did, and this I am putting 2 conditions, the geometrical one, that is the Casimir, and the dynamical one, that is a conserved quantity. This is the way that I could find the B. I don't have a systematic way yet. And the Chaplygin ball has exactly the same effect. This B is doing exactly the same. It's taking the conserved quantity and putting this conserved quantity into a Casimir of the reduce of this bracket here. So this bracket, both this and this bracket have as Casimirs all the conserved quantities of the system. So one more observation is that, well, you can see that this Chaplygin ball, what we are having here, is an exact form. So this Chaplygin ball is verifying stronger conditions that this is exact. And in these cases, when this is exact, also is the case of the snake board and the disc, the rolling disc. When this is exact, we can describe the almost symplectic leaves of our bracket here, of this bracket. So this is what I'm going to do now. The idea is that we have this non-holonomic system, and what these examples are verifying is that they have a normal subgroup acting, this GW, such that GW is, in fact, this W is the vertical space with respect to this GW that is acting. So if we think only the GW action, this is a Chaplygin system. So this is, and if this happens, then this 3 form is really an exact form, and this is the differential of this JK. In this case, we can think about our reduction as a two-step reduction. First, we're going to reduce by GW, and we are going to obtain an almost symplectic manifold here. And here we have the JK term, and here we have our dynamical gauge. Now we can perform another reduction, the symplectic reduction. To be able to perform a symplectic reduction here, again, we need two ingredients. As always, one geometrical and one dynamical. The geometrical ingredient is that H, which is the remaining group here, acts in a Hamiltonian way. And the dynamical action is, of course, that if here we have a momentum, the dynamics have to conserve this momentum. So these are the two conditions. And if we have that B is a dynamical gauge such that this is basic or zero, then we have both the geometric and the dynamical conditions verified. So then we can describe, these are the almost symplectic foliation attached to the twisted Poisson bracket describing the dynamics. This is the two form, the almost symplectic two form on each leaf. Here we have, here in this B, we have all this information, the JK plus the dynamical gauge. So the JK really is having all the non-holonomic information. So this is the big picture. Suppose that we have a dynamical gauge such that, can you see that now I took out all the differentials. So now I want these two forms, B plus JK, to be basic. It's a little stronger than in comparison what we were doing before. So now this is the big picture. Let's start here. This is the non-holonomic bracket describing the dynamics. Now I can perform a dynamical gauge transformation and obtain this bracket. Once I reduce, I obtain this bracket. And then if this is basic, then this bracket will have almost symplectic leaves. And this is the part that was in the previous slide. Here we have this intermediate space that was the reduction by GW. So here we have the canonical two form plus B. This B has the dynamical gauge plus JK. And now, doing symplectic reduction, we obtain this symplectic foliation here. Almost symplectic foliation, sorry. Now, let's come back again to the non-holonomic bracket, and we are going to take out this JK term. So we're going to deform in such a way that we are going to take this term out. What we are going to obtain here is, again, an almost Poisson bracket, but whose reduction is Poisson. Because I am taking B just exactly to minus JK, so this will be 0. So this bracket will be Poisson. What I'm doing here is, since I am taking out this JK in the intermediate K, in the intermediate step, I will have only the canonical two form without this term. And if I do symplectic reduction here, of course, I will have what we always study, the symplectic foliation. So this bracket lambda is Poisson, while this bracket describing the non-holonomic dynamics is twisted Poisson. There is a gauge transformation from this bracket to this one. So what I'm saying is that there is a Poisson bracket whose deformation is the almost Poisson bracket that is describing the dynamics. So they have exactly the same foliation, but we have only this extra term here. So in the case of the Chaplygin ball, that was the ball rolling on a plane, it's very interesting because this bracket here, that is Poisson, is describing the free rigid body. So, and if you perform a gauge transformation, you will obtain the dynamics of the ball rolling on a plane with all the non-holonomic constraints. So it would be interesting to study the dynamical behavior, the relation between dynamical behavior. Are the equilibrium points the same for both structures? And finally, in the last minute, I will show you just the coordinates version of the equations of motion on this foliation here. this foliation exists because this is basic, and so we are counting that the momentum is conserved. So if we write the equations of motion on the Lagrangian side, we are going to write the Routh equations. So the Lagrange-Routh equations in coordinates that are these ones without the green term are the Lagrange-Routh equations for classical mechanics without constraints. Now with constraints that are of these types, for this kind of non-holonomic systems that admits a description by almost symplectic leaves, the equations on each leaf will be exactly the same, but with this term, with this modification here. This modification is the gauge transformation plus the term jk. So the Lagrange-Routh equations really are the equations, the Lagrange-Routh equations for non-holonomic. With this extra term are describing the dynamics on each leaf of the twisted Poisson bracket. But you will need always to modify the original one. Always no, but in my two examples, you need a modification and then a reduction to obtain this foliation and to have those equations describing the dynamics. So I think it was all. Happy birthday, Jair, and thank you.